So let's talk about the use of integrals in ECE. Unlike derivatives that operated on just a function, integrals require a function and limits of integration. And the intuition behind it is that they take the area. So if we have a function that looked, which we worked with recently in the derivatives video, the integral here means we've got one sheet starting at 0 and another sheet that we're moving to the right. And that defines our upper limit. And as we move the sheet to the right, the area between those two sheets slowly increases. So if the sheet was over here, now we have a greater area. All of a sudden now, as we move our sheet to the right, it encloses no more area underneath our original graph, and the integral becomes constant. Finally, when we start to move our sheet to the right of this section, this is a negative area, and it has the greatest amount of negative area in the beginning, so it will start off decreasing the fastest, and after a while it adds less and less negative area, and we end up with 0. And this red graph is the same as the one that we had in the derivative video. Talking about limits for another moment, hopefully it's clear that if we have this function and we want to evaluate its integral between, say, this point, we'll call it A, and this point, B. Maybe we're also interested about the total area of it between A and C. We can see that the integral of our function, let's call this axis t, between A and C is equal to the integral between A and B, which visually would be this region, plus the integral between B and C, which would be that region. Let's say that we are given a relationship between a voltage and a current, and that relationship is one of a derivative. So you take the derivative of the current to get the voltage. And say we want to go in the opposite direction. So the reflexive thing one might do is to take the integral of both sides like this. And then we find out that the integral of the derivative is, of course, just the plain current that you want to find. And now that equals the integral of the voltage. And while that's not wrong, it's not complete either. Because what are we missing on these integral signs? We're missing the limits. So what are the limits of this? We didn't need to have limits when we were talking about the derivatives. But when talking about the integral, we do. And the integral that we need is from minus infinity up to wherever you want your time to be. And then the math people will object, saying you can't have this variable t and this variable t at the same time. So just to be entirely correct, I'll rewrite this with a dummy variable. And this is correct. You take the integral of your voltage between negative infinity and t, and that will give you the current, if the original relationship was that the derivative of the current is the voltage. Okay, there's one more point I want to make that is the synthesis of everything we've done so far in this page, and it's actually a pretty common problem in electrical engineering. We're going to see equations like this all the time. But the problem is that rarely do we know v of t for time, for all time, going back to the age of the dinosaurs. We just don't know what it is. So it's really common instead that we're faced with a different problem. We know what the current is at time equals 0. And we know what the voltage is for time greater than or equal to 0. And we want to find out what the current is. And so we begin by applying this equation. It's the integral from negative infinity to t of v of, we'll write it the right way, v of tau d tau. And initially we think we're stumped because we don't know what v of time is for time less than 0. But we can use this up here to rewrite this equation in two parts. And the first part says it's equal to the voltage integrated between negative infinity and 0. And the second is it's the voltage integrated between 0 and t. And the interesting thing is that if I was to ask a different question, what is I of 0, you could put it in this equation. You'd say, well, by this equation, which we know is true, it's equal to the integral between negative infinity and 0 of v of tau d tau. And now look, that this and this are the same. And because these two things are the same, that means that I naught has to be the same as this. So we will rewrite this as I of t, therefore, is equal to I at time 0 plus our integral of v of tau d tau. And the cool part is that this we know what v of tau is, that's a tau. We know what v of tau is, we know what voltage is for time greater than 0, and we know what this is. This is part of the problem that's given at the very beginning. We call this our initial condition, or our IC, and that is in electrical engineering how if you know a derivative relationship, you can convert it into an integral relationship, even if you don't know all history of the voltage for all time less than 0, as long as you know what that current is at time 0. If you understood that, skip the video ahead to the last slide. If you didn't understand that, watch the next slide where I explain it in more detail. So a problem we get a lot in electrical engineering is that we know that there's a derivative relationship between current and voltage. And although I'm drawing it that voltage is the derivative of current, over different components it might be the opposite, that current is the derivative of voltage. But just to focus on the math, if we know this is true, then the opposite is that current is equal to the integral of the voltage. And I'm using a dummy variable tau here, because when I fill in these integral limits, I have to go from negative infinity up to t. And I don't want to use the same variable to integrate against as my upper limit. So if you always know the value of your voltage for all time, going back to negative infinity, going back before the Earth was made, then you're set. But we rarely do. Instead of knowing this, which is what we want, we're usually given something else. We're usually given this problem, that we're usually given something else. We're usually given a value of voltage that we know, maybe v of t is equal to 6 e to the minus 2t, which is only valid for time greater than or equal to 0. And what was it for time less than 0? We don't know. Big question mark. But we are told what our initial condition of the answer is. We're told at time 0 that current was, say, equal to 4. So given those two things, can we solve the equation we really want? And the answer is we can by breaking it up into two parts. We can say I of t is equal to the integral over this mysterious region of voltage for negative time that we don't know anything at all about, plus this region of voltage for which we do know something about. And that comes directly from our previous slide over here on the right. So armed with that, this first integral is numerically equal to I of 0. And you can prove that to yourself by evaluating this integral on the left with t as 0. And you get I of 0 is equal to the integral between negative infinity and 0. So now we can say our current is equal to our initial current plus the integral between 0 and t of v of tau d tau. So let's work it out for this one particular problem. For this one particular problem, our initial current we said was 4 down here. And we're going to integrate between 0 and t of our voltage up here, which is 6e to the minus 2. We'll do it the correct way. Since this is tau, we'll call this tau d tau. So this is equal to 4 plus, let's see, the 6 comes out of the integral because it's a constant. We'll apply the chain rule to the minus 2, so the minus 2 comes out. And that's e to the minus 2 tau, and we're going to evaluate that for tau goes from this lower limit 0 to this upper limit t. Maybe now it's clearer why we have to use that dummy variable, because otherwise we'd have t varying between t, and how do we simplify that? So now we can simplify our limits. This goes from minus 2. We'll replace the tau with a t up here, and from it we'll subtract the value of e of minus 2 times 0. So that's going to be equal to 4 minus 12 e to the minus 2t, and e to the 0th power is always going to be 1. So multiplying through, we get a minus 12 times a minus 12 is a positive 12, plus 4 is 16, minus 12 e to the minus 2t. And that's the answer for t greater than or equal to 0. Of course, we don't know what it is for time less than 0 because we have no idea what our voltage is for time less than 0. But if we're given it for time greater than 0, we can solve for the answer for time greater than 0 using this initial condition here. Okay, last thing is to look at the integrals of some common functions that we first investigated in the last video. If we take the integral of a constant, let's write down what we're doing. If we take the integral of a constant, it's going to be the constant times t, if we take its integral with respect to t. If we take the integral of a times t, it's going to be 1/2 a t squared. The integral of a decreasing exponential, by the chain rule that minus a becomes minus 1 over a times e to the minus at. The integral of a cosine is a positive sign, again divided by the derivative of the inside by the chain rule. Notice that the frequency does not change. And similarly, the derivative of a sine is equal to a cosine of that same frequency. The only thing that's changing is its magnitude. So let's talk about the properties. What happens when we integrate a constant times a function? That constant comes right out of that integral, and it's just like we're taking the integral of the original function. So as an example that we did last time, taking the integral of that would be equal to 2 times the integral of e to the minus 3t, which would be minus 1/3 e to the minus 3t. And then you could multiply these things to get minus 2/3. The integral of a sum of functions is equal to the integral is equal to the sum of their integrals. Just the same as it was for derivatives. Not the same at all for the product. The product of two integrals is not the product of the first integral with the second integral. This is hard. So if one of these functions happens to be a constant, it's easy. You just multiply them together. But if they're both functions of time, you cannot take the integral of the first and multiply it by the integral of the second. I see that mistake a lot. And that completes our review of how integrals and derivatives are used in electrical and computer engineering.